This is the first lesson of Unit 6. We're going to be learning about integration, but first we're going to learn what an integral is by learning the area functions and Riemann sums. So, situation 1 is stated here. You have a particle that moves along a straight path with a constant velocity of 2 feet a second. The graph of the velocity of the position function is given above. What is the total distance the particle traveled from 0 to 2 seconds? So if you're looking at this and you think, oh, I traveled 2 feet a second and this is 2 seconds, we know that the distance formula is rate times time. Our rate is 2 feet a second and our time is 2 seconds. So we have our velocity times our time. The velocity is 2 feet a second times 2 seconds. So that is a total of 4 feet that we traveled. One thing to notice is that the area under the vector is also 4. That this is an area. It is width times length, or length times width. The length being the rate and the height being in seconds. And that's one of the things about an integral that we're going to learn later, is that it is an accumulation of area. It's the area under the curve. So going to situation 2, it's kind of the same situation. You have a particle moving along a straight path, but its velocity is increasing as it moves. So that's why we're going up, because our velocity is increasing. And again, our x-axis is in seconds. And then the question says, the graph is given above, what is the total distance traveled? So kind of reiterating what we did on the first, we want to try to calculate the area here. Now notice, we don't really know how to do this because there's no easy figure to find the area, but we can kind of estimate it with a trapezoid. And if you do notice that we do have a little bit of extra, so this is going to be like an overestimation, but we can use this to guide us, and it's going to build onto another concept later. From Algebra 1 or 8th grade math, we know that the area of a trapezoid is 1/2 times the bases added together times height. Think of it as an area of a triangle where it's 1/2 base times height. But with a trapezoid, you have 2 bases that you combine. So that's how I always remembered it when I was in primary school. So doing the formula, we're going to have 1/2. Here's going to be your base 1, which is going to be 1 unit. Here's your base 2, which is 3 units. And then your height is going to be here, which is also 2. And so if I calculate this, I'm going to get 4 times 1/2, which is 2, times 2, which is about 4 feet. Now that was the same as the last problem, but notice that we do have a little bit over the curve. So this is kind of an overestimation. So we'll write it like with the less than symbol. Okay, so key concept 1. The area bounded by the rate function gives the accumulation of change. And the rate function is the curve here. And when we say bounded, we just mean that there's a starting and stopping point. One other note is that the accumulation can be positive if it's above the x-axis. If there's some area down here, that is a negative area, which is below the x-axis. And for non-linear or non-geometric shapes, we're going to have to use calculus to really find the true area here. And that's what we're going to try to build on. So let's re-examine situation 2. It's the same concept, but now we're giving the velocity function. So we're given an equation that describes its velocity. So let's examine this again. Before, we had kind of an overestimation. Now, if we break it up into more shapes, we get a better approximation. So let's say we're trying to break this up into 2 trapezoids. So we have 1 trapezoid there, and we will do this in green. We have our second trapezoid in green. But notice the error. We're only going to get a little error up here for the green trapezoid and a little area for the pink trapezoid. So if we do more than one shape, we get a better estimation. So let's recalculate using the new one. So we have our pink trapezoid plus our green trapezoid, and we're going to calculate the areas of each. So again, we're going to add the bases together. So the base here is 1. I don't know exactly where this is right here, but we have an equation that describes the height. So if I want to know exactly what this point is, I can substitute 1 back into here. And if I do that, I'm going to get 1 squared times 0.5 plus 1, and that should be 1.5. Okay, and then the height is just going to be 1. And so if I do this whole area, I'm going to get 2.5 divided by 2, which is 1.5. I'm sorry, that's 1.25 for that pink trapezoid. And we're going to do the same thing to the green trapezoid. So I already did this here. I already plugged in 1 and got 1.5. And then my base 2 is going to be here, and that is actually equal to 3. And again, we're going to times the height, which is 1. So this calculation is going to be 4.5 divided by 2, which is 2.25. And if I add these together, I get that it is 3.5 feet. So that is technically a better estimation than the previous because I had less error. There was less overestimation. But again, this is still an overestimation slightly because if I draw a straight line, there's going to be a little bit of area between that straight line and that bottom of that curve. In calculus, we can use other shapes besides trapezoids. We can use rectangles. Now in this example, this is going to be an underestimation. We're still missing area here and here. But again, we are estimating. But if you do notice, if I take more and more squares, my estimation gets better and better. So if I took 4 squares, or 4 rectangles, I say square, but I meant rectangles, notice my error has decreased a little bit. If I take 8 squares, it will decrease. If I take 100, I keep saying squares, rectangles, then the error keeps decreasing. So the more and more shapes I use, the better my approximation becomes. And here that brings us to key concept 2. So approximating the area with Riemann sums. And again, that's what this is. Riemann sums are adding a bunch of rectangles together to find an area. And there's kind of 2 things you need to know. One is how many rectangles do I use? The more is always better. And then there are 3 types of rectangles I can use. One's called the left point, one's called the midpoint, and one's called the right point. And it's used to find the height. So like here, I use the left point as the kind of the height of the rectangle. And when I do this one, I go over, and then here, that left point uses it. I could also use right points. So let's say I'm going here. But notice that when I use right, I'm going to have a little bit of error. That's an overestimation, right? And so that's using right endpoints. Again, because I'm using the right side of the rectangle to figure out the height. This would be an overestimation. The previous one was an underestimation. And then the midpoint is using the midpoint of the rectangle. So we're going to practice this a couple times with different Riemann sums. So it says use a left Riemann sum. And what that means is we're using the left point as the height of the rectangle. Use a left Riemann sum with 1 interval to approximate the area under the curve. So if we just use 1, we're starting from 0 to 2. So again, we're trying to approximate this area. Now using 1 rectangle is a bad idea. So you start at 0, you're going to go up until you hit the curve, and that's the height of your rectangle. And so that's going to be my estimation. So my rate was going to be 1, because again, this is my rate here, times my time, which was 2 seconds. So this gives me an approximately 2 feet or whatever unit it is. It doesn't say what unit, so we'll just erase that. Again, this is a gross underestimation of what total area is. Okay, so now let's look at it with two subintervals. Same question, we're using left Riemann sum from 0 to 2, but we're going to use two equal subintervals, which just means we're using two rectangles to estimate the area. So my first rectangle, I'm going to go up here. There's my first one. My second one, we're going to draw here. Again, we're using the left side as the height. So again, my total distance, we're estimating using these areas. We're going to use rate times time, which is 1 times 1, plus my second. And my rate is going to be approximately 1.5 times time, which is 1. So this is going to give me 1 plus 1.5. So this is going to be 2.5 units. And again, the total distance is going to be technically greater than that because there is some error. There is some stuff we didn't consider, but it is a better estimation than what we did here. There was way more missed area. And again, we're finding the area because technically the total distance traveled is the area under the curve. Okay, so for the example 3, we're going to use right-handed Riemann sums. We're going to do two equal rectangles to estimate the area here. So we'll do our first one in green. So the rectangle, we're going to use the right endpoint for the height. And so estimating this, the rate is going to be about 1.5 times 1. And then we're going to use a peak rectangle, use the right-handed limit to determine the height. The rate there is going to be 3, and the time is still 1. And so to calculate this, I'm going to get 1.5 plus 3, which is a total distance of 4.5. And this is going to be an overestimation. So we know that the total distance is technically less than 4.5. So it's somewhere between 4.5 and 2.5 is the actual answer. So here's one of the key concepts is the more rectangles we use, the better our approximation becomes. So obviously, if you use one rectangle, there's a lot of area you're missing. If you use two, you capture a little bit more. There's still some missing area. If we use 4 rectangles, we're getting better, but there's still some missing area. This is 8 rectangles, but notice how our margin of error keeps decreasing. And if we want to know the exact area, we need to take infinitely many rectangles. So if we do an infinite number of rectangles, we will get the exact area under the curve. And just a note, this is using a left Riemann sum because the left side is the height. Okay, so getting into some formal notation, you can use any number of rectangles in rectangles. Remember, the more you use, the better you are generally. When we say delta x, this triangle symbol means delta. That means the change in time. So that's like your unit of time. And when we say f of x, we're talking about the height or the y value of the rectangle. It's the height of the rectangle. Right? So if this is 3, the height is 3, and that's what f of x is. This is how you write it, the area of change, the area of each rectangle. It's the y value times the change in time. Again, the height is the y, the change in time is x, the area is length times width. And then when you're trying to total the area, we use this summation notation. This is a capital sigma symbol. It means add up all of the rectangles with a height of y and a width of x, or the change in x. All right, and this is going from 1 to how many ever rectangles. So in this picture here, this would be a 3, right? Because we have 3 rectangles, 1, 2, 3. That's the height of the rectangle, of each rectangle, and that is the change in horizontal distance, or the change in time. And basically, this just says add the first one to the third one. So this area plus this area plus this area. To get an exact answer, you have to do an infinite number of triangles. Or I keep saying triangles, rectangles, an infinite number of rectangles. So again, this is an infinite number of rectangles that are added together. It's still the same formula here and here. It's just this is an infinity because we're not taking a finite number. We're taking an infinite number. And then this symbol is going to drive you crazy. This is the integral symbol. You're going to get very familiar with this the second semester. And what this means is we are just finding the area using an infinite number of rectangles. So this is the area from B to A. So B to A. There's the height of the rectangle, and that is the width of each rectangle. So key concept number 3, whenever you see this, it is an accumulator, which means you're just adding up areas of rectangles from that point to this point. This is the function, or which is the height of the rectangle. This is the width of the rectangle. So example 4. So let's say we are trying to find this area. How would I write this using integral notation? So we have our integral. And again, it's from this value to this value. You always start to the right. So it's from x to 2. And then we're going to have the function name here, which in this case is h of x. And then we need to know the width of each rectangle, which is going to be dx. So example 5, use integral notation. So there's my integral. So starting at 4 and going all the way to -5. So that's the area under the curve here. We need to know the function's name, which in this case is f of x. And then what is the width? It is dx. Again, this is the width of the rectangle here. This is the height of the rectangle. So f of x is here, dx is here. It just depends on how many we're doing. Okay, so let's try this using tables. Again, we're not going to get into formal integrals yet. You will know shortcuts to this eventually. Right now we're just playing around with the idea and showing you where it comes from. And we're going to do this the long way, the hard way, and then eventually you're just going to learn rules that make this quick, just like with derivatives and limits. So here's a table. You have a large department store that's open from 9 a.m. to 9 p.m. That's 12 hours. So this is 9 a.m. This is 9 p.m. The rate that people enter the store in people per hour is modeled by the function Pt. So again, we already have the derivative where t is the number of hours since 9 a.m. So this is 0 hours after 9 a.m. This is 12 hours after 9 a.m., which is 9 p.m. And the table values contains certain times for t. Use the data to answer the following. So used a left Riemann sum with 3 subintervals to approximate this area. So again, we're trying to find the area under the curve, which is the total number of people that went into the department store. Right, so we kind of have a curve that looks like this. We're trying to estimate this area. Right, I don't know exactly what this looks like, but that's what you're trying to do. And we're going to use Riemann sums to figure it out. So we need 3 subintervals. And this is from 0 to 5. So we're not doing the whole time. We're only doing this time. We're using Riemann sums to estimate the total people for the first 5 hours the store opened. And we're going to use a left Riemann sum. So I kind of drew a table down here, or a graph down here. Now notice I only included these values on my number line because this is the only values we have. So let's kind of plot these points. So 0 and 11 is going to be somewhere here. 2 and 30, 4 and 54, and then 5 and 26. 5 and 26 is going to be there. So basically, I am going to use this interval, this rectangle, and this rectangle to estimate the total number of people. And we're using left Riemann sums, so my height of my rectangle is going to be that 11. So that's going to be my first rectangle. My second one is going to go all the way up here. And then my third one is going to be there. And I'm sorry for not being able to draw straight. So that's the areas we're going to find. And you guys can look at this and calculate it, but let's write it in formal notation. So we're going to say Riemann sums. There's 3 subintervals. The minus means that it's from the left. That's going to be our notation we're going to use. So we're adding up from 1 to 3 rectangles. My equation is going to be the function times time, but we're going to call it times the change in time. Again, this means change. So that's my notation for the first one. Again, I want the height at 0, and this is my width is 2. And if you look over here, the width is 2. And my height at 0 was 11. So my height at 0 was 11. So this is going to be 11 times 2. So that's my first rectangle. I have 2 more to do. So we're going to say this is at 2. And then my change in time is going to be 4 minus 2. And again, I'm getting them from here. My change is 2. The width of the rectangle is 2. My height was the value at 2 because I used 2 to determine the height of the rectangle, which in this case is 30, plus my last rectangle, which is going to be the height at 4. And then the change in time was 1, because again, it's from 5 to 4, which is 1. The height was 54. And if you add all these together, that's 136 people. It's 22 plus 60 plus 54. So that is an estimation on how many people entered the store for the first 5 hours after opening. Moving on to example 7, it says use a right Riemann sum with 4 subintervals, and it gives us our 4 subintervals to approximate the value of the integral from 12 to 4 of the function p of the derivative of p with respect to time, dt. Include units of measure. One of my rectangles is going to be from 4 to 5, so that's going to be an interval of 1. My second one's going to be from 5 to 6. My other one's going to be from 6 to 9. And then my last one's going to be from 9 to 12. So formal notation, we're going to do a Riemann sum of 4 rectangles using the right endpoint. And so in sigma notation, that's going to be from 1 to 4. List the function, p prime of t times the change in t, or the change in time. So my first subinterval is from 4 to 5. So using my right hand or my right endpoint, I have to see what value I have at 5. Now if I come back up to the table, I see that I'm at 26. And so this is my first rectangle. I can see that the height is 26. The base is 1. So I know that that's 26, but let's write it formally over here. So I have my y value at 5, or the function's value at 5, times the change in time, which is 1. So that was 26 times 1. Plus, we're going to do the second rectangle now. So second rectangle is going to be, again, using the right endpoint to find the height. So we need to find the height at 6, which is going to be 21. So that's my second rectangle. It has a height of 21 and a width of 1. And again, this is the value at 6, or the height at 6, the height of the function at 6, times the change in time. We know that that was 21 times 1. Plus, we need our fourth rectangle. We're going to go from the right endpoint of the rectangle at 9, which is 44. This height is 44. Now notice that the change in time here is 3. So again, this is p prime of 9 times the change in time, and the change of time is 9 minus 6. So that's going to be 44 times 3. And then the last rectangle is at 12 from here. So we're going to go this way. The height at 12 is 0. So my last rectangle has no height. So it's no height times 3. So if I finish this off, I have 26 plus 21 plus 44 times 3, which is 132, plus 0. And all of that should be approximately 179 people. And again, I'm taking these units, which is peoples per hour, times hours. People per hour times hour leaves me the units of people. So 179 people entered the store between 4 and 12 hours after the store opened, which is from 1 to 9 p.m. All right, example 8. Last question for this part. There is a part 2 that's going to be coming from this section. So it says approximate the value from 0 to 12. So from when the store opened to close of p prime of t dt using a midpoint Riemann sum with 3 subintervals as indicated in the table above. Using correct units, interpret the meaning in the context of the problem. Remember, 0 is when the store opened at 9. 12 is when the store closed at 9 p.m. Now, using midpoints, so I need 3 subintervals or 3 rectangles. So when I'm using 3 subintervals and using a midpoint as the height of the rectangle, if I start out with the first values, I see that my first rectangle is going to have a height here, whatever value this is at 2. My second rectangle is going to be in this interval because the midpoint of 5 is going to be the height. And then my last rectangle is going to have 9 that dictates the height. So let's draw this. Let's find the value at 2, 5, and 9. So at 2, the height is going to be 30, and then 26, and then 44. So I labeled my heights. So here's my first rectangle, my second rectangle, and my third rectangle. So you can calculate this right now, but let's use the notation. So we're doing a Riemann sums with 3 rectangles. I'm going to put mid there, and that equals the sum from 1 to 3 of p prime of ti times the change in time. And again, the I is here because of this. Like when I plug in the first one, that's the height of the first rectangle. When I plug in a 2, that's the height of the second. When I plug in 3, that's the height of the third. So finding my first, it looks like we're using the height at 2. So it's p prime of 2 times the change in time. The change in time is 4 minus 0. And the height at 2 was 30 times 4. So that's going to give me 120 plus we have our second rectangle that has a height of 26 using 5, the midpoint of 5. The change in time in this case was 4 to 6. So that gives us height of 26 times 2, so that's 52. Plus our last rectangle, which we use 9 to define the height because that's the midpoint. And the change of time was from 12 to 6. The height at 9 was 44 from the table. The width of the rectangle, or the change in time, was 6. So 44 times 6 is 264. And so if I add 264 plus 52 plus 120, I'm going to get a total of 436 people. Now, I'm not going to write it, but it does say interpret in context of the problem. So you would say what this means is that 436 people entered the store from time equals 0 to time equals 12 hours. An alternate way of saying it is this function means that 436 people entered the store from 9 a.m. to 9 p.m.